So now that we've started talking more about differential equations and specifically indefinite integrals, how they're just doing antiderivatives, and remembering that we have to put plus c because these aren't definite and the constant doesn't get canceled out by subtracting in the definite integral. Uh, we need to start talking about some of the more advanced derivative rules and how we undo them. And the one that we're going to look at in this video is the chain rule, or composition of functions. So if I just look at the integral of x to the fifth with respect to x, the antiderivative of x to the fifth would be 1/6 x 6 plus c. And I can check that by taking the derivative, and I do get x to the fifth. But I do have to be careful with these, because what if I have antiderivatives that involve composition? So here, if I had x plus 2 all raised to the fifth power, as I actually have composition, I have an x plus 2, which is its own function, inside of something being raised to the fifth power. And that can cause some issues. Now, one thing we could do is, it is a polynomial. We could multiply that all out using binomial expansion, Pascal's triangle, whatever method you want to choose. But that just takes a lot of time. What we could do is what's called integration by substitution, or you'll sometimes hear it referred to as U substitution, where what we do is we say, let's take the inside of our integrand, where we can notice there's some composition involved, one function plugged inside another function. Let's say that U, hence the name U substitution, is the inside part. So the x plus 2 is inside of the fifth power. So let's say U is the x plus 2. Well, I then want to take the derivative of U with respect to x, which would be 1. And then I want to solve this for dx. So if I multiply each side by dx, I get that dx is equal to du. And now I do the substitution part. I'm going to replace x plus 2 with u, and I'm going to replace dx with du. So I get that this is now the integral of u to the fifth du. And I know this is a good substitution because all of my x's are gone. If I have any x's left over, this is not a good substitution. Now, the x's can disappear through the act of substitution, or they could disappear because as I'm replacing things, division will cancel some of the x's out. But the key is once I've plugged everything in and done some simplifying, there are no x's left. So here, antiderivative of u to the fifth with respect to u would be 1/6 u to the sixth plus c. But I'm not done, because we were specifically asked at the beginning, what's the integral with respect to x? So I need to change back to x's. But we know that u is equal to x plus 2, so I just plug x plus 2 back in for x. I get 1/6 times x plus 2 to the sixth plus c. And here is my antiderivative. Going up the scale in complexity, sometimes it may be a little bit tough to decide what is inside, what is outside. So there may be some trial and error involved. Here I've got the integral of x squared plus 2x minus 3 all squared times x plus 1. For some people, they would think, well, let's say u is equal to x plus 1. But then we have this x squared plus 2x minus 3 that we can't do any substitution on. Yeah, we could factor that, but there isn't an x plus 1 that we would have there. So it doesn't really help me to say u is equal to x plus 1. So let's say u is equal to x squared plus 2x minus 3, which I can see is inside of the squaring. So if u equals x squared plus 2x 3, I find the derivative of u with respect to x, which would be 2x plus 2. And I solve this for dx. So multiplying each side by dx, and then I would divide each side by the 2. I have 1 over 2x plus 2 times du. Now I'm going to plug all of these into my integral. So I'll have the integral of u squared times x plus 1. Then replacing my dx, times 1 over 2x plus 2 du. Now, at first glance, this doesn't look good because I do still have x's left over here that aren't canceling. But 2x plus 2 is the same as 2 times the quantity x plus 1. And if I do that, the x plus 1's do cancel, and now my x's are all gone, and I just have the integral of 1/2 u squared du. And this I can go ahead and find the antiderivative of, which would be 1/6 u to the third plus c. But again, I need to have this with respect to x. So this would be 1/6 times the quantity x squared plus 2x minus 3 cubed plus c. And there's our antiderivative. Now, again, like I said, sometimes it is difficult to see what u should equal for substitution. And sometimes it's even hard to notice that it should be substitution. So, for example, the tangent of x. We know the derivative of tangent is secant squared, but we don't know of any function that has a derivative of just tangent. But I could think of this as sine of x, the integral of sine of x over cosine of x. And this actually is a case where u substitution can be used. Now, for some people, they say, well, let's say u equals sine of x. Well, derivative of u with respect to x, cosine of x. So dx would equal 1 over cosine of x du. Well, if you do that, you get the integral of u over cosine of x times 1 over cosine of x du, which is so close, but those cosines do not cancel out, so that is not the correct u substitution. We need to pick a different one. So let's say u is equal to cosine of x. Well, derivative of u with respect to x would equal negative sine of x. So dx would equal negative 1 over sine of x du. So now when I do my substitution, I would have the integral of sine of x over u times negative 1 over sine of x du. And the signs of x's will cancel out. I'm going to move the negative out in front here, so I have negative integral 1 over u du. And now we can go ahead and find that antiderivative, because now I don't have any x's left. So the negative out front is a constant multiple. Antiderivative of 1 over u. I know it feels like we should be doing power rule backwards here, but if I do that, I end up with u to the 0 power times 0, which is 0, and that definitely is not the correct answer. But antiderivative of 1 over u is the natural log of u plus c. Changing it back into x's, it's the negative natural log of the absolute value of cosine of x plus c. Now, you may have noticed that I threw in absolute values around my u and my cosine when I did my antiderivative to natural log. And the reason for this is the domain of the natural log is positive numbers. So I don't know enough about u to know if u is positive all of the time, so I have to force u to be a positive number when I take its natural log, which is what the antiderivative does, or I'm sorry, the absolute value does. And then same with cosine. I know cosine is not always positive. So the absolute value forces it to be positive, so I can always take the natural log of it.